Hello, everybody, and welcome to our talk about Apache Kafka at scale. My name is Maulin, and I work at PayPal as a Kafka infrastructure team's lead. And our scale of using Kafka at PayPal is about 1 trillion messages a day we serve through Kafka. And we are one of the top 7 largest deployment of Kafka in the industry, in the world. So before we begin with the particular agenda for today's session, this is just a slide I kind of referenced from one of my public presentation recently to show you the Kafka scale at PayPal today, where as you can see, we are nearing very fast toward having 1 trillion messages a day through Kafka. And we host about 50 plus Kafka clusters in production, having about 5,000 plus topics, and majority of our deployment of Kafka clusters is on pair methods. And as you can see below here in our Kafka journey timeline, we have come a long way using Kafka over the last several years. And we consider ourselves one of the mature users of Kafka at this scale. So to start with our agenda today, we will talk about the use cases where Kafka plays a very critical role in the industry. And then we'll talk about few fundamentals about Kafka ecosystem. And then we'll discuss the design implications. And then we'll, have other key areas of discussion as you see here. And then, we'll talk about challenges at scale that you need to be aware of. So what is Kafka? Kafka is a open source streaming platform developed by Apache Software Foundation. And it originally started at LinkedIn and before it became the open source project. And it is basically a high throughput, low latency platform for handling real-time data feeds. It was named, interestingly, after a novelist of 20th century named Franz Kafka, the photo that you see here. And Kafka implements a custom binary protocol over TCP, which makes it equivalent of HTTP, like application layer protocol. So Kafka plays very critical role in several of use cases in the industry. For example, if on your website, if you want to do activity tracking for the user, either click-throughs or you want to run user experiments based on, you want to offer A/B testing kind of functionality. And that data needs to be seeded from the website. And then you need to analyze the results for A/B testing, for example. So those use cases, Kafka, does really very well. And, it has been used in many companies like that. Other use case is metric or log aggregation, where you can imagine tons of metrics are flowing from one system to another, and the log aggregation logs, in log files distributed across lot of machines. You need to aggregate them and then make some meaningful decision out of it. And without really waiting for the log to be aggregated and consolidated in huge gigantic files and stuff. Also, in last couple of years, Kafka has been really being elevated in the use in the stream processing world, where you see the applications like Apache Spark, and it is a very similar application where if you need a stream of data is coming to you, and you want to have, tumbling window kind of sessions where you want to collect some data over period of 10 minutes or let's say 20 minutes, and then you want to analyze that data, then those kind of applications are, have really started to use Kafka streams. And other use case is to, do the near real-time analytics on the data that you collect on your platform, which was typically, before Kafka world, it was typically be done with, ETL batch jobs workload, where, you would move the data from site to analytics platform, and in range of like hours or days, you might get some results. However, with Kafka, that has changed a lot. So you get the data in real time, and then, you can run your analytics and make your business decisions quickly based on those live stream data. And for example, you could use the login data for user or payments activity on your website for, fraud detection in near real time, or, within minutes you can take decision instead of waiting for like a day where, and the risk and the stake is high, because within a day, if you detect a fraud, it's going to cost you a lot more money than if you detect the fraud within like a couple of minutes or maybe half an hour. So let's talk about few fundamentals of Kafka. And to begin with, at very high level, these are the components that are involved in Kafka deployment in the overall ecosystem. Of course, the Kafka cluster is in the center of all of that, and it has a hard dependency on Apache Zookeeper to maintain certain metadata about Kafka cluster. However, in recent versions of Kafka, they have slowly started working toward eliminating this dependency and go toward hosting all the data or the use cases that Zookeeper is used for today within Kafka cluster itself. And that leaves us with basically, on left side, you see the producer and consumer on the right. And that represents the whole ecosystem of set of producer applications, set of consumer applications surrounding your Kafka cluster. Now, if we take, one level deeper look at these boxes that we saw in the previous diagram, you can imagine that, you could have like horizontal scale achieved on each of these boxes, and you have lots of boxes under producer apps, you have a lot of boxes under consumer app, and of course Kafka cluster is comprised of several brokers, and the Zookeeper the same way with multiple nodes in it. However, the important thing to understand upfront about this is that every application box, producer or consumer, when they talk to Kafka cluster, they need to be able to connect to every single broker in the cluster. Why this is important? Because depending upon as you scale your system with Kafka usage, and your company's ecosystem has some peculiarities and restrictions, and you could run into a scenario where some of the applications need firewall to be open in order to connect to Kafka cluster. And that is going to limit your ability to easily flex up Kafka cluster or the producer or consumer app who needs to go through firewall, because as soon as you add machines on either side, it's going to break because you did not make firewall rule changes. And that could really impede your flexibility. So this n square kind of connection topology is important to understand. And the other implication of this n square topology is that, as you can see, every broker is getting inbound connections from every other consumer or producer application box, which means they are all it basically translates into the sockets, and socket translates to file descriptors on the operating system, which means out of the box, the design, you look at this and you realize that you are going to be configuring high number of file descriptors to be allowed to be open on the Kafka cluster. So let's talk about how Kafka organizes your data in terms of basically it allows you to organize your data in logical abstraction called topic. And you can create different topics for having different kind of data, like user.login topic for login related events, payments topic for payment related events maybe. And at a physical level, the way it translates to is that a topic maps to as n partitions, and each partition has n segment files. And here, partitions are basically nothing but folders or the directory on your operating system, and the segment files are obviously the files. So, and they have default limit of like 1 GB, which is a configurable value. You can change it depending upon your needs. And again, here also, since these are all files and directories, they contribute to the file descriptors in the operating system. And as you can see, right, as you scale number of partitions in the Kafka cluster to thousands of them, and each one having segment files, right, you can imagine the requirement around number of open file descriptor you need to maintain. In terms of the actual message that Kafka models, it is relatively straightforward, where it has set of headers which are optional. You could have message without headers, and it has a payload which is consisting of key and value. Again, key is optional, and the way so the next diagram will talk about how these messages are really stored. So Kafka basically stores all these messages on this, in the segment files in a log, append only log structure. What that means is, here, for example, I've shown like, T1 topic with 2 partitions and T2 topic with 1 partition. And as you can see, like different partitions are getting different number of messages depending upon your load pattern of ingestion. And it appends each message in a sequential order. And there are 2 key pointers that I have put in the diagram, which you need to understand. One is the log n pointer, which essentially means that it is the last successfully appended position in the partition log, which means the next message will go after that pointer. And as you can see obviously from the diagram, different partitions could have different log n pointers basically. The other pointer is high watermark, which we'll talk about in the next replication slides. But at higher level, what it means is that pointer tells that until that point, it is safe for consumers to consume messages. And beyond that, it will not allow consumer to consume messages, which is the delta between high watermark and log n. We'll talk about this during the replication discussion. So let's talk about replication now. So just like any distributed system which wants to offer you highly available system, basic premise in that system will be the replication of your data, so that it can have multiple copies of your data. So if one copy goes down, you can go to other copy without getting downtime in your applications. And you keep your applications keeps running transparently, and that's the goal of having high availability. And Kafka follows similar principle, where it allows you to configure replication factor at a topic level. And once you apply that configuration, what it means is all the partitions belonging to that topic will get that replication factor, meaning that many replicas of those partitions will be maintained. For example, in this case, we have topic 1 with 3 partitions with replication factor 3. And the diagram below, kind of clarifies what it means is, there's 3 copies of partition 1, 2, and 3 each. The other part here, important to understand, is because there are multiple copies of your data, there has to be some way to, somebody needs to be master maybe. And that master copy of partition in Kafka is called a leader partition, which I have indicated with letter L here along the boxes of partition in the broker boxes. So as you see here, broker 1 hosts the leader partition T1, P1, and that's the leader of that. And broker 2 and 3 have copy of T1, P1, and they are called replicas or followers. So what Kafka does is, let's say, for example, all the producer or consumer traffic has to talk to the partition leader in order to produce or consume. Which means if I were to send a message or consume messages from T1 P1, I will talk to broker 1. And if I have to consume and produce messages for P2 partition, I will be talking to broker 2. Now, when one of the broker, let's say, goes down, let's say broker 1 goes down, then other broker, either broker 2 or broker 3, will be chosen as the leader of the partition, new leader of the partition. So T1 P1 could, be led by broker 2 or broker 3. And your applications, the Kafka client library automatically detects this change of metadata that, hey, now broker 2 is a leader instead of broker 1 for T1 P1. And then from that point on, all the communication happens like that for sending data or consuming. So transparently, you can imagine the partition failed over to another broker without impacting your application. Now, these copies that you see here and the copies, the brokers that host them are considered to be part of in-sync replicas. So in-sync replicas for partition 1, for topic 1, will have broker 1, broker 2, and broker 3. Why they are called in-sync? Because in the replication, as the leader partition is getting the data from the producer, the follower partitions on broker 2 and broker 3, they keep fetching the data to replicate the message. And there is some, because it is a distributed system, you can't really guarantee that a message which comes to T1 P1 on broker 1 is instantaneously available on broker 2 and broker 3 in the copies. You can't really guarantee that, which means there is an inherent gap that is going to be there between the master copy or a leader copy and the follower. This gap is configurable within the limits of, you want to say that, hey, up till certain number of delta of messages or the timestamp of the messages, a copy can be considered to be in sync with the leader. We'll talk about it in the next slide of about the implications of this. But so now you can imagine that there are 3 brokers in the in-sync replica set for each partition here, and they kind of operate within that configured delta. And as far as they operate within that delta, they are good. They will be considered in-sync replicas. The other, the small yellow kind of a note that you see here, why high watermark on the left, is because I want to make sure that I come back to high watermark. So the high watermark pointer is basically, as the producers are producing to leader partition, the data keep getting replicated to followers, right? And when the data gets replicated to all the followers in the ISR set, it is safe for Kafka to say, now that message is safe for consumers to consume. Why? Because let's say if it doesn't do like that, and as soon as the leader gets data, it moves the high watermark to say, hey, this message is good for consumer. And if that leader goes down, then the broker 2 or 3, let's say, who becomes the leader and doesn't have this data, it will be confused that, it is consumer is supposed to consume a message number 10, which doesn't exist. So, because of that, it keeps the high watermark lagging kind of behind the log n. Log n moves faster depending upon your produce rate, and high watermark moves based on your replication speed. So now we talked about the in-sync replica set, right? That 3 brokers are in sync, considered to be in sync without, as far as they remain within some configurable bound of messages lagging, right, in the replication. That configuration here I have highlighted in the blue, which is, replica lag time max milliseconds. But what is important here is to understand that in a distributed system, let's say a broker becomes slow, or it becomes, it crashes for a while before it comes back, then they are going to lag significantly compared to the leaders. And that lag makes it ineligible to remain in ISR side. So instead of 3 brokers in the ISR side, now you are left with 2, let's say. And because of that, that condition is basically called under replication of that partition. In itself, it's not a fatal condition. It is natural to have these things happen all the time, depending upon your network speed and ingestion and lots of other factors. But the important part is if you keep seeing lots and lots of under-replicated partition, you need to pay attention and try to see how to fix that. Because at some point otherwise, you may end up in a situation where out of 3 replicas in ISR set, one by one, everyone goes down. And as I mentioned before, that if all of these go down, for Kafka, there is no way to choose a new leader. There is a complexity about choosing unclean leader and stuff, but for now we'll keep it aside. But assuming, let's say, Kafka cannot choose a new leader for you, what it means is you are going to stop producing or consuming from that topic partition, and you have you create an availability impact for your customers. So offline partitions, and that is called offline partition because there is no leader which can take messages or give messages to consumer. That is a fatal condition. You do not want to see that in life. It does happen sometimes, but it's a fatal condition. Now let's talk about the other fundamentals on the ecosystem of client side, where in order to bootstrap a client application for Kafka, there are a couple of configurations which are important to understand. One is the bootstrap servers. What that means is, out of, let's say, 10 brokers in a Kafka cluster that you want to connect to, you pick 3, let's say, and put it in a list in the bootstrap server configuration in your application, with, of course, either with the host name and port or the IP and the port. And then when your Kafka application starts, it is going to look at this configuration, pick one of them, most likely the first one, and then make a metadata call to the Kafka broker that it detected as a first broker. And then from that point on, it will find rest of the metadata about Kafka cluster, like number of topics, number of partitions on each topic, who are the leaders, which are the ISR set for each partition. So it will get all that metadata in that call. And from that point on, whatever you have in bootstrap servers doesn't kind of matter much until you restart the application again. Because from that point on, it has established connection to every single broker, basically. The other configuration, which is important to understand, is serializer and deserializer. So, as I mentioned before, Kafka is implementing a custom binary protocol over a TCP layer, which means your custom data types needs to be converted. There needs to be some way to convert them to byte array. And on the producer side, and on the consumer side, there needs to be some way to convert those byte array into custom object again of message, which defines the message. And this applies for the message key as well as message value both. If we go a little bit into details of, let's say, so now let's say you have producer application which started with all these bootstrap servers and key serializer and value serializer. And then you are ready to make a send call with a message. These are the 4 components here in the diagram that I showed that are important to understand, because the sequence also matters here. So the first one that gets invoked within the send call is set of interceptors, which are basically pluggable interceptor classes which your application can plug in and you can do anything which is application specific to you. And once those are all invoked, it goes to a serialization phase, and that is also a pluggable interface where you can define your own serialization, which will convert your custom type to byter. And then it is followed with a partitioner call, which is also a pluggable class, but there is a default implementation. And that pluggable class is basically going to determine that given each message, which target partition it will go to. And the last bucket here is the batch preparation, because Kafka doesn't do one message at a time, doesn't send one message at a time to broker. So it batches the messages that you keep sending. So the caller, now imagine in the next slides, we'll see some of that code. But you keep calling send, and then it buffers the data and then prepares the batches based on your configuration of how big you want the batches. And then at some point it will do the send in order to have a higher network I/O throughput. And the below here you see the default partitioning logic, which I think is pretty self-explanatory. The other aspect in producer to understand is the modes of the send call. And I would request you to not to look into too much into the code example here, and don't get distracted a lot, versus let's just talk about this. What are these three modes and what does it mean? So first one is the fire and forget send, where what it means is that a producer makes a send call and then doesn't care about any response whatsoever, which means if you send and if you get an error, producer doesn't get to, and that's why it's called fire and forget send, which obviously practically most likely is not used at all, I hope. But sometimes some cases are really fire and forget, then you can use it. Other mode is sync send, where you send a message and then immediately you have a get call here, as you see in the red line. That means that you send and you wait immediately in a sync fashion, which works well, not a problem, but obviously it has an impact on throughput, because now you are per message, you are waiting. Send, I wait. Send and I wait. The third mode is probably the most popular and common mode of sending. To have what you want to do is keep sending messages and let producer object buffer them, do the batch preparation and send it, and then tell you as callbacks that, hey, whether a particular message went through or not. And that's the callback here. And you get callback for success and failure both. And that's the kind of template of detecting the error case versus success. So send mode is one part of the important thing about producer. The other is there are other additional configurations apart from bootstrap servers and serializers, which are X, for example. So the configuration X defines that how are you going to interact with the Kafka broker, which means if you have X configuration as 0, what producer library, this is assuming all Java, what it does is it will not wait for any response from the producer, which is obviously going to give you very high throughput, low latency, but obviously possible loss, because you don't wait for any response, so you don't know what happened. With X1, what it guarantees is that the leader of the partition to which producer object is sending the message is going to act that it got the message successfully. This is probably the most commonly used configuration, I would say. If you need a reasonable durability guarantees with low latency and reasonable throughput, not like ACOL totally bad, but not like the third configuration, which is ACOL, where you need very high guarantees of durability, where the way that mode works is if you configure your producer with ACOL, it will make sure that when you send a message, it will wait for every single copy in your ISR for that partition to acknowledge that message. So the leader broker will do that waiting. So you send a request to leader broker, and then leader broker waits until all the replica gets message, and then it says everything looks good. Obviously, you will get throughput impact because of that and little bit higher latency, but you will get higher durability also. The mean ISR also plays important role here when you configure XOR, and I can take that in Q&A for a little bit more details on that if you wish. The other configurations are basically the batch size, which I mentioned, like how long, how big you want batches. And obviously you want Kafka producer to do automatic retries when there are some intermittent or retriable errors, right? And then there is a retry back of MS configuration to tell you, like, to tell the producer how long you want to wait before next retry. The last configuration here is delivery timeout millisecond. And since, when you will read Kafka documentation, you will realize there are like tons of configurations. And this configuration simplifies the contract between, like, as a customer of the producer, client of the producer, and producer actually. To say, within this timeout, if I don't get a success of a message, it is failed. It is failed beyond repair, which means all the retries are done, everything is done, there is no hope to get it anywhere now. And you need to be ready to handle this timeouts. So now, we covered few basics about, producer side of the configurations and how it works. Let's talk about consumer a little bit. So consumer, there is a sample code I have put here, which works pretty much, similar to producer in sense of how it gets initialized. You provide a properties or hash map of to the constructor of the consumer. Then in second line here, what you see is subscription to list of topics. What that means is that a consumer is interested in getting data from these topics. And then beyond that, you just start a while loop, which pretty much goes infinitely on, and you keep pulling the Kafka cluster to give the messages to you. And as you keep getting messages, you keep processing them and move on. This is a little bit a simplified code, obviously. We'll talk about the commit mode and acknowledgement from the consumer in following slides. And just like producer, what happens as soon as you call poll is, and it gets the data from broker, is to deserialize them and then invoke the interceptors. You can observe that interceptors were first in the producer, and in consumer, the sequence is reversed, where deserialization happens and then intercept. And then it returns, basically, after these things, it will return the data, which is the consumer records line here, as a return of poll method. And then you can process your messages. Now, as with any practical application, you would expect that you should be able to do scale out of your application on consumer side to increase the processing throughput. And when you want to do that, how are you going to make sure that Kafka sees all of those boxes under one application as one logical consumer? And that is done using consumer groups. And you can specify the value of the consumer group in the group.id configuration. For example, you can say application 1, application 2, whatever you want. And then all the machines where your consumer runs with that group ID configuration, it will think that you are part of the same group. And then it will do the partition assignment and give messages accordingly. Why we need consumer group is because in your context of the ecosystem, you could have one application who is interested in some certain set of topics, and there is another business application which also wants to use the same topic and data. However, their use of the data and the business needs are completely different, what they do with the message. Which means they are not the same consumers. So logically, they want to separate that consumer using different value of a given group ID. So they could say application 2, for example, and then Kafka will treat them as a separate consumer group. So let's talk about little bit on scale out. What happens when you scale out a consumer group with more boxes on let's say you have a holiday readiness plan and you want to make sure you have enough processing power on consumer side. So on the left here, what you see is initially your consumer, let's say, have 2 boxes and Kafka topic 1 has 4 partitions. And the assignment of partitions is like on the left diagram that you see. Then when you want to add 2 boxes, what it will do is when you add these boxes, given the same group ID in the configuration, and when it comes up, it will send a request to Kafka broker and say, hey, I'm the new member of this group. Same thing will happen on when box 3 starts and box 4. And then Kafka says that, okay, I sense new members in the group, so let me stall the consumption of the whole group and reassign the partitions to which partition data I will give to what client box. And that stall and then reassignment of partitions. And then once that is done, it will say, okay, now good to go. All the consumers can again start consuming. And in this shuffling, you could see, as in the diagram, that partition can go anywhere, basically, get assigned to any box. This process of doing this reshuffling and assigning partitions again is called rebalance of a consumer group. And that could also happen if, let's say, you just had 4 boxes and you do rolling restart of consumer for some reason. Then that results into the same behavior, that you have a consumer rebalancing happening upon each box restart, because it leaves the group and joins back. So now the reverse case of scale in consumer group, let's say you had 4 boxes and you were having nice little assignment there, 1 partition each box, and then 1 box permanently goes down, let's say, or for some reason you have to flex down based on now you don't need that much capacity. Then what happens is, again, similar process of rebalance. As soon as the box leaves the consumer group, Kafka reassigns all the partitions to be consumed. And then based on the new set of members, it processes the consumption. So we talked about having 2 different applications consuming from same set of topics and how it treats the both of them as different consumer groups. The way it keeps tracks, however, for each consumer group, like for each partition of each topic that consumer is consuming, how it is going to keep a track of where they are in consumption. That is done through a concept called, keeping the offsets for the consumer group. So those offsets, message offsets for each partition, for each consumer group is maintained in an internal topic called consumer offsets. And as you can see that, obviously different partitions are getting consumed at different rate because the ingestion rate could be also different, processing rate could be different. And high watermark is also there for each partition, which is regardless of the consumer group. And each consumer group offsets will not go beyond the high watermark. And it will wait. If it hits high watermark, then it is going to wait until high watermark moves and makes more data available for consumption. So there are a few more configurations. There are a lot of configurations in Kafka for consumer also, but these are, I would say, like the most important ones you must understand. And one of them we already talked about, like group ID. The other is the mode, which decides like how the consumer acknowledges the message to the broker that, hey, I'm done with this message. The third and fourth are related to like how many records you want to fetch in the pull request, as well as what is your SLA around making a poll call, process it, and come back to the poll call. If you remember that while loop, infinite while loop that we had. And this time configuration determines how stable is your group. So because if you cannot meet that SLA, Kafka is going to think your consumer threads are dying, and then it will rebalance, and that instability could be problem. And the last two configurations are around similar aspect of liveliness, that you can configure heartbeat interval, which means the consumers are always going to send heartbeat requests to the brokers, and there is an interval within which you want to configure that every 3 seconds or every 5 seconds you want to send that. And session timeout is basically on the broker side. It will say that, hey, if this consumer has session timeout of 10 seconds, within those 10 seconds, if any of the consumers do not respond with heartbeat request, I'm going to consider those members dead. And then I will start rebalancing. So these are, key configurations that you must understand well. So the second configuration in that slide we talked about is the acknowledgement of consumer. And there are two modes basically, auto commitment or manual commit. Auto commit pretty much looks like our original sample that we started to explain consumer with. Just subscribe to topic, run a while loop, and don't worry about anything else. Which means Kafka will internally do the commits for you. The second alternative is basically to have enable auto commit mode off and then let consumer decide when to commit. And you give control, basically consumer takes control of when to commit. Then there are pros and cons of each, and it can be, this is a very important thing to understand when you write consumer code, that which way you are going and what are the implications and how your code will behave based on. Now let's talk about, the design implications, because any system you consider will have design implications based on how it is designed, because every system is designed to address certain set of use cases, not for all. And there are some bottlenecks based on the design. So for Kafka, one of the key things to understand is, since Kafka has all of these segment files and stuff, an operating system puts the page caching layer between the applications who want to read or write and the actual files. And the data which is available in page cache will not be read from disk. It can be just served from the page cache and it will be fast. So that operating system optimization is what Kafka heavily relies on, which means if you have high throughput use case of having hundreds of thousands of messages per second, then you are going to have certain set of consumer applications which are very fast because maybe they have different downstream dependencies. They have not a lot to do with the message. It just, let's just does some counting. Versus some other applications which could be heavily on processing that message and calling like 10 other systems in downstream. Those could slow down. And for some applications, if they go down and when they come back, and if it asks for data which is a lot older than what your page cache has, it is going to result in page fault. And then if now you can imagine a situation where high throughput ingestion is happening on your topic, the certain set of consumers which are like pretty much up to date on the data consumption, and one or two consumers which are lagging a lot, or history kind of load of a consumer. And contention between the fast consumers and the slower ones, or asking the ones which are asking for very old data, is going to result in page thrashing. And that can really, really kill your cluster in a cascading failure case, because one reader will go down because of page thrashing, and then another broker will become leader, that will go down, and then in like couple of hours you may have the whole cluster down. So there's something to understand that how it works. Not that it's a limitation in any sense, right? It's like, we have been operating at a scale a lot and we don't have this scenario in last several years. The other optimization is called zero copy optimization, which is not Kafka specific. It's just general operating system level concept. And you can find more details here in the link here from IBM article. But in essence, what it means is when you want to, let's say, send data to consumer, you are going to, let's say you have it in page cache, you are going to bring it from that buffer, kernel buffer, to user application namespace of Kafka, and then write it to kernel buffer of socket, and then it will go out to consumer socket ultimately. And there are 4 context switches involved in doing all this. And that really is costly. So Kafka optimize on zero copy, where it allows Kafka to make certain system calls to directly copy from kernel buffer to outbound socket, and reverse way for producer. However, when you use TLS, this zero copy optimization doesn't really work, because you need the encryption, decryption, and the keys are with kind of client and stuff. So there's a lot of work has been done around this area, like, primarily by IBM and Facebook, who use zero copy much before than Kafka, and they did a lot of work on modifying Linux kernel to support and make it efficient when you use TLS, and you can really take advantage of zero copy. But this is something you need to take into account when you measure your performance. You need to understand that there is a limitation and explore avenues to optimize for it. The other part is, sensitivity to the flickering consumers, which is basically how we talked about consumer rebalancing, right? As soon as the consumer even gets restarted, then, it becomes unstable, and then it needs to say, hey, rebalance. There is recent work has been done, for example, because this could be really detrimental in case of like Kubernetes like deployment, where pod keeps, coming up and going down, coming up and going down all the time. And that really instabilizes the cluster. So some work has been done, link keep 345 here, to avoid those simple scenarios. Rebalance is still a reality, but there are certain scenarios it can avoid that. And that's the work. The other part is to understand that, consumer doesn't do message level acknowledgements. It does offset level acknowledgement. Meaning, if I consume 10 messages, I'm going to say, I'm done with offset 10, what Kafka will interpret that as saying, okay, all the messages until 10, 0 to 10 are done. If for some reason, number 5 message I could not process and I ran into exception or something, Kafka doesn't know, and Kafka will think you are done with it and it will not give you that back. So we have to take care of how do you make sure you put it a retry logic, and you need to understand how to get around. The last is, it's a contextual thing based on if you are really on bare metals, where because Kafka says there is a broker hosting partitions on the disk, which means the broker's processing logic, compute, and your storage are tied to one broker. Which means if your disk goes down, your broker does also go down. Which means you lose storage, you also lose the compute power. And that could really be challenging. There are some options like if you talk about cloud, then in GCP you have persistent disk, which you can kind of attach to different brokers. In Amazon cloud also there is you use the EBS storage, and volume can be detached and attached to other brokers. There are but depending upon your context, you need to be aware of this. So let's talk about the retention part of it. Like, how does Kafka determine when to delete data, purge data, and stuff like that? So it offers you 2 policies: the time-based policies, where you can say, I want to expire my data after 10 hours of the original timestamp of segment file creation. Other mode is to say, okay, if my segment files go beyond 2 GB, I want to clean up. So based on one of these, Kafka will trigger the cleanup. So, but before we talk about the cleanup, how it works, one other important concept you need to keep in mind is the lock compaction. Because remember how we talked about messages having key and values, right? And when you have key and values in the messages, there is a potential to be able to save the disk space. Because if the same key keep getting newer values, just like the Java's hash map, where if you keep doing put call with the different value with the same key, it's going to override the previous ones. Similar concept of compaction comes here. That in a segment file you had n messages, and then a cleanup thread which runs, which will determine that some compaction needs to done, then it will shrink your segment size, but it needs to rewrite the segments because it's append only structure for so now how does the cleanup work? So cleanup essentially happens via the background thread which keeps getting invoked periodically based on the configuration you provide. And it looks at a configuration called log cleanup policy. This is all on the broker side, obviously. And that value could be delete, compact, or both in a comma separated. And when you do delete, all it says is, okay, look at the retention policy. Either it is data size driven or time based. I will look at that policy and delete based on that policy. If you have a compact value, then it will say, oh, I will try to compact only and no deletions will happen. So it will reduce the segments, but not really delete any. And when you do both, it will first compact and then it will apply the policy to say, okay, is there a chance to reclaim some of the old segments and delete them based on your retention policy? So other, important aspect in Kafka is the mirroring of data. So let's talk about when do you need mirroring really. So if you have, one cluster in the whole company, not much volume, maybe you don't have DR, maybe you are fine. But the use cases where you really start thinking about mirroring is when you want to do DR. So you can imagine the primary site and the disaster recovery site, and you want to make sure that all the data that comes to primary gets replicated to disaster recovery site so that in case of DR of applications, when applications move over to DR side, your data is available. And they don't lose the processing of the data which they were not able to catch up. Like consumers are typically slow, right? It cannot catch up with producing rate because it has to really do something. Producing is just send. So the other use case is, when you are doing migrations within this, like on-prem, you are setting up a new data center, let's say, or you are going from on-prem to cloud. Then, in certain cases, you will want to simplify your, producer client ecosystem movement. And at that point, you want to make sure that you mirror the data to make it available so that you can move different applications at different times without having them lose any data. The other is sometimes, within a company policy based on that, you could have security requirements where, certain network boundaries cannot talk to other set of network boundaries. And all the producer consumers lying in one side cannot talk to Kafka cluster on the other side if they want to consume data or produce. In those cases, you separate, like you establish two clusters and then you do mirroring to make the data available locally within that network boundary or something. And the last but not least is, the application sometimes require data aggregation. So you can imagine that from the upstream of producing of the data, you are getting data in multiple data centers. And you have different regions, let's say, and you have different clusters in that. However, certain applications want to do aggregation over all this data. Now you have two options. Either you make application talk to every one of the data center, or you aggregate them and put it in one place where application can just run their logic from. So what are the options available in order to achieve the mirroring? So there are few I have listed here where, one is the Kafka offers you utility called Mirror Maker, which is, legacy Mirror Maker, where it is basically a pair of, consumer and producer. It consumes from the source cluster, produce to the target, and you get mirrored data. However, it is replaced with Mirror Maker 2.2 in recent Kafka versions, which offers a lot more functionality, and it kind of, fixes some of the challenges we had with legacy Mirror Maker. Other option for mirroring could be Kafka Connect framework, because Kafka Connect framework, what it says is you can have any source to Kafka connection or Kafka to any sync connection. So you can move data from any system to Kafka or from Kafka to any other system, like Oracle database, MySQL, Amazon S3, God knows what. Right? Lot of options. So you can easily think that, yeah, what if I have source as Kafka and target also as Kafka, right? So you could use Kafka Connect to do mirroring also. And there are some other open source libraries like uReplicator, Brooklyn, which are, uReplicator open source by Uber and Brooklyn by LinkedIn. So you can look at them and then decide which one really fits your use case. And there are other commercial vendors like Confluent who provides you Confluent Replicator, which is built on kind of Kafka Connect, but it offers you the vendor support and more enhancements. So you can choose based on your context which one will work better for you. However, whichever you choose, there are few key things you need to watch out for. The first one is to, how do you make high throughput guarantee with the mirroring? Because mirroring is basically you are doing in order to make sure your data is available on the other side for people to really use. And if that lag is like in hours, it's not going to really solve the businesses. So you need high throughput mirroring. You need monitoring around how much mirroring lag you have and what is the latency you see. You need to also make sure that sometimes the use case end up in, mirroring from source cluster to target, and then again from target to source, back to source. And in those cases, if the same message keeps going from source to target and in circle, it's not going to help. So you need to be careful with this. The other key part of the mirroring is generally the consumer offset sync up requirements, where you can imagine your source cluster as set of consumers. And as we talked about, they have consumer offsets and they know where they are in the consumption of partition data. In case of the DR, let's say it goes to a DR cluster, then suddenly all these offsets are all messed up, because when you mirror, you can't really guarantee the offsets are kept as same. And because of that, and there are many reasons for that, you can't really technically guarantee one-to-one. And because of that, when you move over consumers, how do you make sure that you start from where you actually left in the original source cluster partitions? The other part is, there are some topic metadata like, retention, partition count, that are all there. So when you mirror the source cluster, if you change the retention, does it mean you have to change the target one? If you change number of partition on source, does it mean you want to change the target also? So if you want to keep them in sync, then you need to think about it. And depending upon any solution you use, these are the things you should keep in mind and see how it works. And most of the solutions have kind of one or the other way to achieve these things, except like legacy Mirror Maker has a lot of challenges. It doesn't have a lot of these features. So what are some challenges at scale that you need to keep in mind? So, when you start typically a Kafka adoption in your company, it will be like, you have a one cluster, you have a cluster, people are starting to onboard, you have some volume, things work beautifully for a couple of months. And as you start hitting scale, you start seeing challenges. And in order to make sure that you are not reacting to the problems after you already scaled a lot, you need to keep in mind that you need a way to make sure your capacity is going to be sufficient. Either you are on-prem or cloud. If you are in cloud, the challenges will be how do you elastically maintain that capacity so that you don't pay a huge bill. At the same time, you don't lose the processing also. On the on-prem, different kind of challenges for capacity you need to consider. So you need to be careful in onboarding the topics into your system, knowing and know your applications, have some onboarding process where you can kind of really know who is doing what. Sometimes the use cases are not even fit for Kafka sometimes, and that doesn't really work well for customers at that. Then other most important aspect is you need to be able to control who does read and write from your clusters and rate limit them. Without that, because Kafka clusters, if they are multi-tenant, you are going to have different applications coming in. And if one application has issues causing the cluster going down, you can really figure out the bad actor and then come out of an incident. The other part is, as you grow your Kafka footprint, you are going to have different clusters depending upon your context of the company. You could have clusters in different regions, different, virtual boundaries of zones. And then you need to make sure you have a visibility into what is all that, what topics are hosted on what clusters, what the metadata looks like across the whole ecosystem instead of just within a single cluster. The other important part is the monitoring and alerting, where you need to make sure that Kafka has tons of metrics published as JMX. There are some system metrics at OS level. Then how are you going to process all that data and make meaningful sense out of it in order for you to have right alerts and then actions on those alerts? Because without that, you will be lost in hey, I have Kafka problem, but every time it seems a new problem, for example. And you don't know. Before your customer reports, you have no idea how to knowing that there is a problem. The last part, but not the least, is the how you need to make sure your administration and deployments are also manageable and easy to do. Because as you increase your footprint, you are going to have challenges how to really run admin commands like repartitioning and stuff. How are you going to deploy? Where are you going to keep binaries of your Kafka stuff? And then if you are on managed solution, it's a different thing. But otherwise, you need to be careful with this. Let's talk about monitoring at higher level. How Kafka allows you to monitor things. So this is based on the assumption of Java client-side library on producer consumer. On the broker side and all the Java client side, there is a plugin called Kafka Metric Reporter. And what Kafka client or the broker code does is it keeps publishing JMX metrics to this reporter. And then you can use this pluggable class to say, okay, now I have my own reporter to move data of this metrics to somewhere else where I can, which is my metric system, like Prometheus. So you move all this data to metric storage system. And then depending upon the solution and the context, you could have either Prometheus provides you the visualization tool, or you use something like Grafana to visualize these metrics. But some or the other way, you need a way to see those and then kind of do some aggregation based on the time you want to see the metric. And the other part is the alerting system based on these metrics, where you want to configure your rules in terms of standard deviation, 99% percentile variations, and any custom thing that you build, and then feed these alerts into like incident management system like PagerDuty, where you can configure your on-call support and make sure that whatever you do here, you have some way to for the operators on the incident to react to those alerts, because if I get an alert and I have no idea what to do, it's not going to help really. You could have thousands of alerts through PagerDuty, and pretty much people will start ignoring them because there are just tons of. So you need to really focus and figure out what you really need to monitor on. So the next slide highlights some of the areas where you need to pay attention to, like, but not all. Depending upon your context, you could really have some more or some less based on this. So there is topic metric, there is URP, which is under replicated partitions, offline partitions, consumer or mirroring lag in terms of like how far behind you are. Then actually data is available for consumption. And the client perceived availability is a very important concept, because if you think from a Kafka operator that everything is good, but if clients cannot even connect, they think Kafka is down. The other things are like zookeeper connections, system metrics like page swapping and CPU, memory, OpenFT counts, IO weight. There's tons of these things around there. And JVM metrics, like you need to be able to ready to run with JFR reports and heap dumps and so on and so forth. And this is the last slide of the presentation. And what this talks about is at a very high level, as you grow your footprint of Kafka, as I mentioned, you are going to have clusters in different regions, even different geos, and then you have zookeepers to manage, and based on the solution of mirroring, you would have more boxes to manage. And all of this, somehow you need to be able to cohesively manage better, because you need to run admin command like the blue line you see here, topic creation, repartitioning. You need to be able to deploy and spawn new clusters. You need to be able to set up the security and access control rules in zookeepers as of current implementation of the ACLs in Kafka. You could you want to manage your mirroring capacity as well as the configuration, like in which set of mirror makers you add what topics to get mirrored, and if you need a more mirroring capacity, because remember, if mirroring doesn't have high throughput, low latency, it's going to be a challenge. So there are tons of these things you have to really manage, and you need to focus on developing control plane to see how are you going to do that. There are a lot of different ways to do it, and you have to really pay attention to it upfront. As you start growing, you need to sense it and start focusing on it. So I think with that, I would open up for question and answers. And I will stop my screen share. And I would like to call out one thing, that currently I work for PayPal for Kafka team. However, beyond that, I don't really do any private consulting. So that's just a kind of a call out that I wanted to do. And as usual, like PayPal is in growth mode. It's like we release our recent results. It was great. So we are hiring. So please feel to drop out the line to me if you are interested in working on some of these challenges. With that, I would like to thank you, and let's start Q&A. All right. So there are some questions I see here, and there are upvotes, so I'm going to take in that order. So one of the question is how to prepare or answer Kafka-related interview questions with respect to system design if you don't have experience working on it and interviews go deep into it. So it's a very interesting question, very valid. See, these things are not really like, if you really don't have experience working on something similar, not necessarily Kafka, because in any distributed system, concepts are similar, like how replication works. There are modes of like, is there a master mode of replication? Is it like, single master and other replicas mode? And all of these variations of possibilities of implementation have pros and cons. And if you start looking into it, you realize that a lot of systems are very using basic building blocks. For example, write-ahead logging. If you look at Apache Pulsar, if you look at Apache Bookkeeper, if you look at Cassandra, they are all using very similar concepts, which are not new because of what Cassandra is maybe or what Apache Bookkeeper it is. But the conceptually write-ahead log makes sense in a certain scenario, and those are commonly used. So what I would recommend is, don't get only pivot toward the Kafka part of it, but try to understand the most important in this presentation. I would like you to focus on is the design implications, and try to read about different systems, and then you will have better idea of what a system at scale or with a lot of these guarantees of high availability are designed with, and how they are designed, and what are some trade-offs people make. Like for example, Kafka has a trade-off that all the read write goes to leader. If leader goes down, there is to be a new leader. Even though you have copies in other brokers, you can split the read traffic. Why? Because there is a lag between the follower and the leader. And that's where the challenge is. And some other systems allow you make sure that they write upfront to two of the instances where you can go to any of them for read from that point on. So you can split your read traffic. But that's a design of Kafka, which is different. So I hope I was able to answer this question in a helpful manner. So I will move to another question. I am interested to know what use cases does PayPal use Kafka for? So it is basically every single use case that you saw on the slide here. We use it for analytics, near real-time analytics. We use for risk and fraud detection. We use for website activity tracking. We have log aggregation use case. We have streaming applications. So it's pretty much these high-level buckets of use case. And primarily, I would say all the ETL workloads like ETL is extract, transform, and load. And those are kind of batch world of doing the processing, moving data to Hadoop and then doing analytics. Those have moved to Kafka a lot. So you would see more and more of those applications going to Kafka. But when you talk about Kafka streams, you have to consider other parallel technologies like Apache Flink, Apache Spark. How do they work? There are nuances and differences, and how they work. So pay attention around those things. Right. So next question is, does Kafka support transactions? Example, I have e-commerce application, user create. So pretty much I'm going to ignore reading rest of it because the gist of the question is, does Kafka support transactions? So yes, in recent versions of Kafka, there is support of transactions, but it's you have to go deep down into your use cases, talk to your on-site Kafka experts and really see where it goes. In general, I would say Kafka is very good for high throughput, low latency applications, and transactions are not high throughput, low latency. Because when you make payment transaction, as a user, right, when you put your card online, you are very careful not to click pay button again, right? Because you are okay with little bit of latency. You will wait 5 seconds maybe before you say, okay, this is a bad system, right? Which is why transactions are costly. They are tailored for guaranteed data. And if you want to do those things in Kafka, yes, there are recent versions of Kafka libraries which kind of allow you to do up to a certain extent. But I would really give a hard look at your actual problem and then see, because it's a matter of cost. In order to support Kafka transactions, you will invest 10x money compared to not using Kafka and use RDBMS. Then it will boil down to that cost level, because yes, you can use it if you really want, but then there's a cost, and that cost is always the pros and cons deciding factor for that. The other question is, what are the industry competitors for Kafka and how does Kafka stack up against them? So very interesting question. There are other systems like, Apache Pulsar is, I would say, head-on competitor with Kafka because they offer very, very similar functionality. And again, you have to really go into design depth of each enough to understand how they are different, because at a surface level they will do the same thing. And then how do you decide which one works better for you? Which means you need to really understand the implications of design of that system and see which use case what implementation works better for you. So there are, like, in my mind, from top of it, definitely Apache Pulsar is a competitor, and dig I've deep dive into it a little bit to understand how it works. So you have to do your due diligence and really make a call. And the stack up part, right? How does Kafka stack up against them? It's kind of lot of contextual thing around it, because everybody runs benchmarks in different ways. You really kind of ideally need a neutral third party to say, hey, I have no interest in A or B, and I'm doing a benchmark, and then let's see. And then the numbers and setup are really different based on how things are designed. So, okay, the next question is how Kafka is used in geographically distributed application. So again, it boils down to you know, your deployment topology. Like, for example, if you have data centers in US, your data centers in Europe, if your data in general writes needs to remain local versus reads can little bit far away and could sustain more latency maybe. But it really depends on your context. Meaning you could have Europe and US deployment of Kafka, and then you could have a use case to say, move all this data here for central analysis, like an aggregation use case you talked about, right? So it really depends how you want to deploy. But in general, when you deploy within a specific region, like let's say US West, then you are going to think about how many AZs you have. Do you distribute your brokers across AZs to form one cluster, or do you keep Kafka cluster in one AZ? What are your deployment policies? So it really depends. It could be you can do however way you really want it to be. But the factors you need to consider is the write latency, read latencies, how are you going to sync up the data if you really have requirement of mirroring, and then all those contexts. The next question is, can you talk about some challenges you guys faced on daily basis and how you scale up or solve for them? So again, this really depends on your particular deployment. For example, at PayPal, we are, majority is bare metal deployments. So our challenge is, and we have figured out a sweet spot of Kafka usage where, for example, we don't allow more than 3 days of retention of data. In 90% of the use case, 1 day or 95 even. And rest of it may be worst come 3 days, not beyond that. Because we don't want to have a situation where kind of applications assume that, hey, I could be down for like 6 days straight and then suddenly wake up and consume like several gigabytes per second suddenly from cluster. We don't want to allow those. So it really depends on your context, but some of the challenges if you are in bare metal world is because you are going to own machines, and when you own machines you might have to keep them up to date in patching for OS patches on regular intervals, which is insane. Like it happens like pretty much every week. For example, we patch about thousands of broker in a week automatically, and then you can find some of these references in my public presentations outside of this also, where we talk specifically in the context of people. And the other part I would like to call out is Kafka, sometimes the question is that, hey, if I just host Kafka in cloud, will my problems will vanish automatically? I would say no, because your challenges are not going to be because how Kafka is deployed as much versus Yeah, you get some advantages in cloud, obviously, the flexibility of capacity and stuff. But ultimately, what your ecosystem is around using Kafka in multi-tenant cluster is what is going to determine your scale of issues. And that is where I mentioned that you need to make sure you have read and write control over who is doing what. You need to have rate limiting. You need to have you need to know what are the clients connecting to it, what are they doing, and if there is a need, you need to be ready to shut some of the traffic down. And those are the things really we see on day-to-day basis, that most of the use cases work well, and one use case which is kind of sometimes not architected right, consuming maybe thousands of topics where it should not have, the way their deployment work, those are the challenges, or apart from certain Kafka challenges. Cool. So other is the N-square connectivity mandatory, or is it the preferred or recommended approach? Very good question. And this is the reason I explicitly call it out. It is not about whether you want it or not. That is how Kafka works. Every client machine needs to be able to connect to any broker. Why? Because let's say your partitions are such that you are only going to talk to 3 leaders, 3 brokers out of 10. But what if dynamically when one broker goes down and a new leader is chosen, if you are not able to connect to those, then it's not going to work. So out of the box, you have to assume that you are going to need to be able to connect to every single broker. Because otherwise, you can imagine your load on brokers could be really skewed, because you say, hey, I just want to connect to 3 brokers out of 10 always, which means you are trying to create kind of a subcluster. And that's not really going to work for Kafka operators to manage it like that, which is why N square is basically the connectivity. So other question is, how is Kafka different from AWS Kinesis? So there's tons of kind of material out there on the web. You will find the comparison of Kafka and AWS Kinesis. And if they were not different, both of them will be named Kafka, right? Which means what I'm trying to say is, every system is designed for a purpose. For example, Kinesis is designed for a different purpose. You could, there are some limitations and there are some optimizations that Kinesis has which Kafka doesn't, or Kafka has, for example. And based on that, they are different basically. A lot of times you might hear that hey, Kinesis is just built on Kafka, but it's not really like that. Their architecture is not the same way. It is different. There are some certain limits which Kinesis want you to understand before you use it. So I would say, there are a lot of blogs and comparison about this. And there are some limitations I know from top of my mind in Kinesis, like, certain number of consumer groups beyond the consumer, like 20 or 200, I forgot the number, but beyond that, it won't scale. Kafka doesn't have that limitation out of the box, at least. There are challenges when you scale with thousands of consumer groups, but it's not really necessarily need to be called out. Versus some of the Kinesis blog, you will find that hey, this is a limitation. So the next question. So we have just a time check. We have 5 minutes before 1.5 hour mark. So we'll try to take as many questions, but within 5 minutes probably we'll call it a session. So the next question I see here is, how can you set up and use Kafka for free to understand it more? Oh, it's damn simple. You just go to Apache Kafka website and they have a quick start guide. You install locally, you are up and running. You can install, you can start 3 brokers, 2 zookeepers, 3 zookeepers locally, everything locally. You can play around, figure it out. But that's a kind of a brute force approach, right? Just start using it and you won't really understand, because you need to pay attention to the design. So I would strongly recommend read the design aspects of that Apache Kafka from their website, and then go into the hands-on experiment, and then really figure out what are the use cases you are trying to look or solve for. And then if it makes sense, then you start investing more into it. So the next question is how to answer this question. What is the throughput of Kafka? The internet says millions of event messages per second, but it doesn't talk about the data size, message event ultimately. So there's a long question, but to kind of, cut it short, yes, it is a tricky question because you can't absolutely answer that it's a contextual thing. Whoever does the load testing of Kafka to say, hey, in my system, I want to figure out what Kafka throughput is. So it's really that contextual, because sometimes it's even harder to push data at the rate you want, because you cannot match the thousands, tens and thousands of production applications which are trying to push data to Kafka. You can't simulate that, which means, you will not be even able to fork that many producers to really simulate the production payload. So there are benchmarks based on the configuration of the benchmark, saying that, hey, we are on this kind of a skew of the machine with, this many GBs of RAM, this much of, SSD hard drives also makes a difference. Your network latencies sometimes make a difference too. Whether you are on bare metal versus VM makes a difference. So there's a lot of contextual thing, and every benchmark that you see will be basically run on some context, and they generally call out what is the configuration they use to find the number. So the next question is, which tool or how do we measure number of messages or message size? For example, in PayPal scenario, you mentioned closer to 2 trillion messages per day. So it's basically, number of messages it's a metric. So Kafka is a JMX metrics called messages in per second, messages out per second, bytes in per second, bytes out per second. And then you just, look at those numbers and you figure out how many messages you are, moving through Kafka. So I will mark this one also done. The next question, this may be the last question or one more beyond that, is the Kafka CP or AP system, and what configuration is supported by Kafka to achieve CA? So very good question. So Kafka by itself allows you go either way, meaning if on a producer side, let's say you really are using for a use case where you can't really afford data loss much at all, like near to 0.0001%, let's say, then you would have to configure your producers with ACOL and min in-sync replicas as more than 1, which is the default value. And on the broker side also, you need to make sure that, are you enabling unclean leader election? So there are tons of configurations that you need to be aware to tune in order to, on the producer side as well as consumer side, which will give you the perception of CP versus, CA versus CP versus AP, basically. So you have to really understand the configurations, what they mean, and then go from there. So, okay. Cool. So the last question is...
Okay, yeah. One last question, Malin.
Yeah. Yeah. So that is, how do you map partitions and topic? Basically, when you create topic, it says how many partitions you want to create. And then it will, under the hood, it will create the required partition folders and segment files underneath. So there are no two different activities that, hey, I create topics, I create partition, and then I map them. That is not how it is. It's just you create the topic. That is your logical abstraction. Beyond that, it's all Kafka will take care of.
Awesome. Thank you so much, Malin. And thanks everyone for joining us this evening for our microclass on Kafka. I hope you've learned a lot during our session tonight. We did have a lot of questions come in, and we did go through quite a bit. Thank you again for participating with the questions. But if you are interested in learning more about Interview Kickstart, we will be posting our link to sign up for our webinar tomorrow. It's tomorrow at 7 Pacific. So if you're interested in learning more, please go ahead and sign up on our link there for our webinar with our co-founder, Ryan. And Malin, thank you so much. Thanks for the awesome session. We all learned a lot, and we hope to have you again.